Okay.
All right. Hey, folks. I guess we'll start as folks come in. But my name is Bryan Kelly, and I'm a Principal Firmware Engineering Manager at Microsoft. And with me today, co-presenting.
Hi, so I'm Yigal Edery. I'm a program manager in the Azure security team. I'm not a hardware engineer. I come from the security background, and we've been working together on Cerberus. So today we'll basically walk you through what is Project Cerberus, why do we think this is critical, and also obviously within the context of OCP, what's the OCP security project and how those two things interoperate, I guess. And we don't have the clicker, so we'll have to...
Use me.
You're the clicker, okay. So here's the clicker. So we'll talk about firmware security in the cloud. I want to put it in the context. There is a big echo here. Who is? Okay. I want to put it into the context of why do we as Microsoft care about OCP security. The echo goes away here. We'll talk about what we see as the current state of the industry in terms of hardware security. Then do a deep dive into what exactly is Cerberus and how it ties back to Open Compute. Okay. So let's start with an interesting quote that Bryan introduced me to. This guy, Hobbes, is a locksmith and an innovator, and he was talking, and he lived in the 19th century, and he was talking about how you can actually exploit existing locks when he was describing a new lock and a new innovative lock that he had. And he was asked, like, why are you revealing those secrets? This is security, and you better not talk about it. And this is his quote, which is basically our mindset. The hackers always know everything we do. That's our assumption. We always assume that security, by not telling what are the holes, is not true security. So we try to come up with a good, secure, cryptographic ways to actually ensure security and not fall into security by obscurity. Open Compute security project was started or announced as an incubation in last February. Go through them. Bryan and so Microsoft and Google are co-chairing this incubation group, and we've been working together to basically come up with OCP specs for security, and the goal is to have the community focus and advance the hardware security platform. So let's talk about why security is even important. So this is just silver, right? This is hardware, and obviously it just should be trusted, and everything there is happening the right way, and no issues whatsoever. It's all in the software stack and up, right? I think many years, we as an industry tended to think about it this way, as the hardware, the server, is this black box that we know what it does, and security starts at the higher levels. Reality is the server is filled with firmware, and firmware is just software. For me as a security guy, I think of it as software. And this software basically loads the system before anything else comes in. And if, as an attacker, you manage to gain control over the firmware, if you get control over the BIOS or the BMC or the NIC firmware or etc., you own the server. Everything that happens afterwards has your code in there, and you can do whatever you want. You can see anything running on the server. It's really now yours. So as an attacker, it's really a dream come true. Within a cloud environment, if you own the server, you own the cloud. You basically are inside our infrastructure. We can't allow that to happen. And no one will actually find you, because traditionally we haven't been investing and looking into hardware security as an issue. So if you are in the firmware of some system, you will be there, you will persist operating system reinstalls, you will persist reboots, of course, power up, everything. You're just going to stay there until someone maybe ends up catching you. So this is real. It's not just an imaginary threat or a theoretical threat. It is real. It is real because attackers get full control over the system. If they attack the firmware, they own the whole server, the whole stack. It is getting weaponized. Attackers and APT groups are actually writing kits to make it easy to exploit firmware. It's not a here is a vulnerability we found. It's here is an SDK you can use to actually put a rootkit that replaces the BIOS inside the system. It's very hard to detect, as I said. It's like not trivial to even know that a firmware was modified, and it's very hard to fix. When this happens, recovering the system back to a good state is not an easy job. Firmware is getting compromised from many years now. I think there are examples here of UFI being compromised. There are examples of a kit that the NSA was using for infecting SSD's firmware. And just yesterday, or the day before, in the news, there was a recent discovery by ESET of the first time a UFI rootkit in the wild. So they actually found true cases of UFI being infected. We always know that they exist. Now we even have the first time incident of actually this was found in the wild. So this is absolutely true. This is happening, and we as Microsoft have to protect ourselves against it. We have to make sure that we have the right security measures in place to ensure that we know that we are running the right firmware. Okay? So let's talk about some of the things that could be done. Again, back to just starting by setting up the context of why we care about this so much, and as cloud providers, what are the threats that we really worried about. So let's start with internet facing. Like if this is our infrastructure, right? I'll try to walk you through the attack scenarios, and this is not comprehensive, but it is a good subset of threat vectors that we worry about and that we try to make sure we address. So the first one would be someone from the internet. So it could be a consumer who is malicious or an enterprise that got compromised and there is a malicious person there and they have some working relationship with us. They would start by the first attack vector. They obviously have access to VMs, right? We offer VMs as a service. If they found some way to escape the VM and get control over the host, they can start changing firmware, right? Because now they have host access, and we need to make sure that even if they get to that stage, that they escape the VM for some reason, which is obviously a very hard thing to do, and we do a lot of work to ensure this doesn't happen, they still cannot compromise the firmware. Another example of that is often we have optimizations for performance that allows VMs to talk directly to hardware. So if we do that, obviously it happens through VMs talking to firmware. If the firmware is exploited in some way, you end up talking to the firmware, finding the bugs there, running your code on the firmware, and again, you own the server. So in this case, it was a VM using device direct access to talk to a disk. If the disk has a firmware bug in it, we get hacked. Right? Next example is when we offer bare metal services to customers. So if you don't have to even go through a VM, then obviously if we allow you to run on a host that we host for you, you can do things like you have control over the host by design, right? You can then leave something in the firmware laying around, and when the same host gets repurposed and basically assigned to a different customer, you have your code on it, right? So you can use the fact that you transition hosts between customers to leave stuff around and attack the next customer that gets the same hardware. Again, we need to make sure that we don't allow that to happen. So these are just like cases of customers or rogue customers using our infrastructure and using firmware as a way to basically get control over our servers. The next vector would be insiders. We run the cloud infrastructure. We cannot assume full trust even in our own people, in our own system. We obviously have a lot of mechanisms in place for physical security, for qualifying FTEs, who gets to work on these environments. But at the end of the day, if someone gets control into the Microsoft environment, we still need to make sure that we protect ourselves against that someone using firmware or leaving some malicious payload in our system and basically compromising the cloud promise. The last one is the supply chain. So we buy hardware from our supply chain. We get them through many different vendors. There are a lot of entities involved in this process. And we can get from the supply chain something that is already compromised, which is the next animation. Right, yes, okay. So we can get a device, a server, that already has rogue firmware on it, and that would get into our infrastructure. And again, we are actually, at that point, we are vulnerable because we've had rogue firmware infiltrate our infrastructure. So these are just like a few examples of how you can get compromised. Tying it back to before, where I said that there are already known ways to do that, and there are weaponized ways to do that. Hackers are trying to do that, and we are a very highly valued target. We are making everything we can to ensure we don't get compromised at the firmware level. So next slide is what can they do. And I want to separate these two classes, two types of threats we basically worry about. The first one is if the firmware has code bug. So if you have a code bug in the BIOS or the BMC or a disk firmware or the NIC firmware, it's just like any other software bug. An attacker that gets to talk to the firmware can use the code bug, can use some kind of a buffer overrun, integer overflow, these kind of threats to get his code to execute on the firmware on our servers. If they do that, then obviously now they have control. And there are ways to address this, right? The first way to address it is make sure that the firmware is of high quality. When we look at firmware in the real world, we are not there. That's not really the case. The firmware was written over many years by many people who are not necessarily security proficient. And we find bugs and we fix them. And we have all of the source code for our firmware, so we can actually do that. But firmware quality, it starts with firmware quality. If the firmware has bugs, they have to be fixed. The second thing about it is that the mentality of you should always assume that there was a breach, and the mentality of a defense in depth is really critical. We need to always assume that even if some component gets compromised, it doesn't mean the whole server gets compromised. I'll give you an example. If you find a bug in the BMC, and you manage to get your code to run on the BMC, it shouldn't mean that you can run any code you want on the server. It just means that you have to contain it to the BMC itself. So defense in depth as a design principle for us is really critical, and we're working hard to make sure that our hardware actually gets there. So these are basically types of bugs that are really about runtime. I can get my code to execute at the firmware level on the hardware. The second class of bugs is where Cerberus actually comes in, which is about persistence. So how can you make sure that you don't end up being able to persist your attack and put the malicious firmware code into our systems and have it stay there forever? Forever meaning even through host reboots or even through an OS reinstalls. We want to make sure that you are not able to do that, that attackers cannot modify the firmware in a server and basically survive those attempts to clean them up. And for that, servers actually need the ability to protect themselves against malicious flashing. And they need to be able to detect when this has happened. And they need to be able to recover, to go back to a healthy state, meaning go back to the good, well-known firmware version that we actually intended to run on those servers. Okay? So we need protection, detection, and recovery, which gets us to where the industry is going in this space. So if you've been tracking the space, NIST has been working and actually published recently a draft of a new standard, 80193, which is about firmware resiliency. And it talks about the requirements from firmware on how to ensure that firmware does protection, detection, and recovery in a good way. Let's first define what protect, detect, recovery mean here. Protections means you want to make sure that you authenticate every firmware update that goes into a system. You want to have it signed. You want to ensure that it's properly verified during flashing, and you want to basically root trust that's hardware rooted in the system, that you can actually ensure that you booted the right firmware, the right signed firmware. Detection means that if something did go wrong and someone managed to find a way through the protection systems, you will actually know about that so that you can act on it, because otherwise they will stay there forever. So detection is those mechanisms for knowing when firmware was modified to a non-integrity state. And then recovery is really about going back to some kind of a gold version that you know about, that you've prepared in advance and said, if something goes wrong in the system and I detect it to be compromised, I know how to reset back to a good known firmware that I trust. Okay? So the NIST draft, which there is a link here, and you all have or will have the decks, there is a link there to a document. It states a long list of requirements of what exactly does it mean to do a protect, detect, recovery in a good way. There is another document that we recently published. So we are also working with a group called CSIS, the Cloud Security Industry Summit, and CSA is part of that. And we recently published a document that you can find on the web that talks about the right interpretation of the NIST standard for cloud providers. The NIST standard talks about firmware resiliency in generic hardware. When we thought about it from a cloud service provider perspective, we had some emphases we wanted to make on what exactly it means for us as in the server scope and for cloud providers. And we published a paper saying, for a cloud provider, this is what it means to do protect, detect, and recovery in a good way, and it's open, and you're welcome to go and take a look. Okay, so in an ideal world, we wouldn't have to worry about that because that was already everything was done, and firmware was booting securely, and updates were always secure, and everything was fine and nice. But reality is different. Reality is that when we are looking at systems in the real world, we find a lot of issues. For UFI, there is secure boot, which ensures integrity at some level, not complete, but the best that exists today in the industry. It basically checks integrity. It doesn't do anything about detection and recovery after the fact. It tries to prevent the attack by trying to prevent loading non-integrity code. That's where it is. It is platform dependent, meaning if you're running on an Intel system or an AMD system or an ARM system, each of them has their own variants, but it exists in some way. The next piece is the BMCs. I recently attended Black Hat in Vegas, which is a big conference for security hackers, I guess. There was a Black Hat talk there that ended with a summary slide of, now is the time to panic. This is really not where it needs to be. I'm really hopeful that within OpenBMC, we get to do the BMC secure and done right from the get-go. But today, the BMC serves as a big backdoor into our servers. That's how we see it, and we are doing a lot of work to ensure that our BMC infrastructure is actually secured. There is no verification, there is no protection, no reliable way to actually know that we're running the right firmware other than the BMC telling you that it's fine, don't worry. So BMCs are not where they need to be. And you have a BMC on almost every server in your infrastructure, I'm guessing even not almost. Peripherals, very dependent on the case and very ad hoc, but generally we see that when we look and we do an investigation of are these secure, we find a lot of issues. And there is no standard way to secure them. So we find issues in NICs, we find issues in disk, we find issues everywhere we look. Okay, so next slide. Okay, so this basically all leads us to Project Cerberus and why I hope that by now it's clear why we even started that. We really want to make sure that we can trust our servers and trust our firmware and know that if they got compromised, we would actually know about it and be able to react and recover. So Project Cerberus is our way to solve this problem for us. It's basically a set of 3 things, I think of it this way. There are a set of platform requirements. What do you need to do to design a system, a platform, that actually will be resilient to firmware attacks? There is a set of requirements specifically for how to ensure firmware integrity, how to make sure that only signed code gets loaded into the firmware, how to be able to recover. And then it's a chip. At the end of the day, it's a chip that helps anyone implement those requirements, which we will start putting on our systems. and we will start working with the ecosystem to put on their systems. And Bryan will talk us through exactly how it's going to work. So now I get to be the clicker.
I think you got to turn yours off. No?
I do?
Oh, well, mine was echoing earlier, but I think they fixed that problem. So I'm going to talk a little bit about the Cerberus chip, what that is, and how it actually works. So as Yigal mentioned, there's a few different approaches to this. So like in the last slide, one is a bunch of specifications about security and how we expect that to work in the hardware. If the processor doesn't natively meet those requirements, then we have a solution to take a small microprocessor that does meet those requirements and marry it with that other processor that doesn't meet those requirements, and we'll get into a little bit about how that's done in a few moments. But the processor, the Cerberus chip, is a dedicated security microcontroller with internal memory and flash storage. It's got some crypto blocks for AES, SHA, public key accelerator, and a random number generator for some additional key entropy. It's got a hardware interface that helps it to interpose onto SPI buses, SPI and QSPI, supporting all modes, 1x4x4, 1x1x4, and 4x4x4. It's got some eFuses inside in it for our public keys and revocation of key manifests and anti-rollback, some fuses for anti-rollback, and disabling certain functionality during the manufacturing process. It's got a puff that it uses. Again, this feeds into some of the entropy. It supports DICE, which is a TCG standard now. It's device identifier composition engine, and that gives us our core root of trust, our measurement, our core platform measurement. As the ROM authenticates the first piece of mutable code, it also measures it and then feeds that, HMAX that with the UDS and gives us our CDI. We'll get into that in a little bit. And then it's got some tamper resistance around the critical areas of the chip. Take that next one. So how it works, typical sketch here of a dual socket server. Those servers would start up and read their flash in. In the normal situation, when we have Cerberus on there, if the processors don't meet the security requirements, we would interpose Cerberus on that SPI bus. It would sit between the processors and the flash, and it would hold reset control over the processor. It would verify and authenticate all of the firmware on the flash, measure all of the firmware on the flash. It would define regions that are write-only regions and regions that are read-only regions, and only use portions of that SPI flash are exposed. If that was a 16 or a 32 meg flash and firmware only resided in the first 4 or 6 megs of that flash, that's all the processor would see. It would only be able to access the regions of flash that it's supposed to be able to access. Cerberus enforces the NIST 800-1983 in being able to protect, detect, and recover any firmware corruption. So how the protection works. So regions are defined in the Cerberus firmware, which are then programmed against the filter interface, and it will allow only read commands go to regions that are defined as read-only. write commands can go to regions that are of the flash that are defined as writable in the Cerberus chip, and regions that are undefined, no access is allowed. As updates come in, it has the ability to authenticate those updates. So a region would have to be defined as read-write to allow an update to go to it. As the update comes through the Cerberus chip, it's capable of verifying the signature on that update. You can play the little animation. It's like this. A lot of the firmware that we have, we maintain this concept of a platform firmware manifest. And the platform firmware manifest is a list of firmware versions and their measurements that are allowed to run on the platform or the processor that Cerberus is protecting. So we might have versions 1, 2, 3, 4, 5, and then in a manifest, if we found a vulnerability that existed in one or some of those versions, we would just remove those versions from the manifest, send Cerberus a new manifest, and those are the only versions that are allowed to run on that CPU. So in the cloud, it allows you to have a mixed firmware environment. So this can play a role in preventing rollback and permitting rollback at the same time. Detection. So how detection works in the Cerberus chip is this is really a block diagram of Cerberus's own secure boot flow, where it'll first authenticate, not to get confused with the platform firmware manifest, it has a key manifest. And it will first authenticate, when a Cerberus chip itself starts up, it will first authenticate a key manifest. And the key manifest contains a list of public keys that have different application usages inside in the Cerberus ASIC. This key manifest, of course, can be changed. There's some anti-rollback fuses for the key manifest, but the public key that protects the key manifest is fused in some hardware eFuses, and as the ROM boots with Cerberus, it will authenticate the key manifest with the fused public key using digital signature verification. It will then take the first key out of the platform firmware manifest and authenticate the first mutable code. The key manifest, of course, is a mutable area too, but the first piece of code that it's going to authenticate will be authenticated with the key in that key manifest. Cerberus will then take the measurement of both the key manifest and that first part of mutable code, and it will perform a key derivation function and extend that to become the CDI that, upon passing control to the first part of mutable code or the second stage bootloader, it'll also pass it that CDI, and then it will measure the Cerberus application firmware. Once the Cerberus application firmware has been authenticated and measured, it will then go on and measure BIOS, BMC, or whatever peripheral that it's protecting, using a very similar method and some of these other keys in that key manifest. That key manifest, the third and fourth keys in that key manifest are used for PFM authentication, which then contain the versions of BIOS, BMC, or peripheral firmware that's allowed to run on the server. If any of those don't check out, then it will go into recovery, which is the next slide. So recovery mechanisms are policy-based. Cerberus also has a notion of policies where we can send to it a policy on what it should do when it detects a failure. Should it just report it, let the system boot? Should it recover the firmware? Should it hold the system in reset or hold a peripheral in reset and let the system boot? All of that is programmable in the ASIC. In recovering the firmware, we actually switch regions, but for all intents and purposes, this little animation shows you something that emulates copying from a recovery area. What we actually do is pivot the areas, and then your update area, which is going to be your active area, will then will allow you to send down an update, and it would actually be updating the area that had previously gotten corrupted. The hierarchy of Cerberus, so the Cerberus design or the philosophy that we had was TPM and secure boot and that kind of implementation helps protect really well against the host processor. And so implementations are different, like the core rooted thrust measurement. Some implementations don't have that. I think on x86 with the TPM, it's well integrated. On other architectures, it's not as well integrated, and that core rooted thrust is missing. Cerberus helps us with that. But on peripherals, in the modern server, a lot of the accelerators are more powerful than the host processor themselves. Some of these actually finish booting before the host processor has finished its firmware initialization and putting in security measures and protection. So we designed Cerberus to be hierarchical, to be able to extend and reach peripherals and microcontrollers that are not authenticated during the host processor boot, and in a traditional system run unauthenticated and unmeasured. There's a lot of microcontrollers out there and controllers that if it's not an option ROM that gets sucked in and executed in the UEFI, it's likely not going to get measured at all or go into your TPM. So what Cerberus does is it provides an all-up measurement of the platform firmware, including the peripherals that we have in there. So the same process extends that we enforce on motherboard CPUs and BMC. We also enforce on peripherals. And then measurements get exchanged back into the master Cerberus, which is the one that's powered on first as the baseboard powers up. And it provides a platform rooted thrust measurement. It has a log very similar to the TCG log, where you can go and, for telemetry purposes, you can go and see what firmware actually loaded on the server or actually booted on the server. The PFM will enforce a list of firmwares typically. That list could be one or more firmware versions that are permitted to load on the system. Which ones actually loaded come from the firmware measurements and the platform measurement. And then if you want to take telemetry a little bit further to see which actual firmware versions are running on it, you can look at the log. Do I have another slide?
Mine?
Is this you?
Yep. Okay. So maybe one last point on the root of trust for the systems and collecting everything together. Back to the cloud scale and what we're actually doing with that data is within the Microsoft Azure, we have an attestation service that then goes in and basically pulls those measurements from all of the servers. And we have this central way to know that we've received cryptographically trusted measurements of what exactly is running in the system. And then we can detect whether some servers is booting the wrong server, even though we have all of the protection in place, and respond even to that. So back to this concept of multiple lines of defense, we always do the best we can to prevent something, but then we always add a layer of detection on top of that to know that if something ended up being broken because of some reason, we know about it and then we can respond at the systematic level. So it all ends up tying back to an Azure level service of attestation that helps us know that we're running the right firmware in our servers. So we basically are building Cerberus for Microsoft systems, but we also took all of the specs, all of the designs, and contributed that back to OCP. And our intent here is to come up with a community open specs for the Cerberus type of functionality that works well for all of the OCP hardware. We would love to see a community collaborating with us on creating those set of specs. We obviously come with our contributions. Google are there and coming up with their contributions. They have a similar project called Project Titan. But together we want to create the open version of that with the community. There is a working group which is currently in incubation that are currently focused on scoping the threats, just like I did somehow for our environment. What are the threats we want to worry about? I'll give an example of an area where we keep still flipping between different interpretations of that is what do you do with the physical attacker? Is that if someone can actually get physically to the server, what can we protect against with the right technology and what requires physical security, and etc. So we're defining the security threats, we're defining the specs for how to do secure boot properly, how to do attestation properly. There is a lot of work ahead of us defining the processes and technology for secure updates, for recovery, for the different hardware interfaces. How would this work? For example, attestation between the Cerberus equivalent of OCP on the motherboard and the peripherals. How do they talk to each other? How do we collect all these things together? So there is a lot of work to do there. And we really would welcome you. If you are familiar in this area and want to contribute, please come in. We meet weekly. And we will evolve those specs together for OCP in parallel to the work we're doing for Microsoft for Cerberus. The last slide before we open it up to questions is, so I think I just explained the first one. And you're welcome to join. And also I want to just finish up with one thing which I often notice tends to be forgotten. Cerberus is about authenticating and ensuring that you're booting the firmware that you intended to. But if the firmware is of low quality, this doesn't really help us. So don't forget that if you're a firmware developer and if you're developing systems, think about firmware quality. We are working together with the Open Firmware group and the Open BMC group to ensure that those right security practices are implemented in open firmware. But if you're developing your own firmware somewhere, please don't forget about security practices. Follow proper security development practices and develop secure firmware. Nothing can replace that. And also the defense in depth concept, which is even if you think you've done something securely, try to think where is the trust boundary you want to put. Like if a component gets compromised, it doesn't need to mean that the whole system got compromised. So implement the right trust boundaries within a system to ensure that potential exploits actually get mitigated in the best way possible. So with that, let me open it up to questions. Yeah. Yeah, I thought you. No? So any questions to me or to Bryan? Yes. I'm supposed to mute the mic because it's recorded.
Do you think that exposing the SPI interface in the meanwhile, like until all that work is done, that exposing the SPI interface of the system that you're trying to audit as a serviceable port, like on the back of the server, that this is a good idea or more like a fool's errand? Just so you can verify from the outside what's on the flash.
Yeah, I don't think anything happens from outside the system. I think you might be thinking that the SPI port is brought off of the motherboard and to an external port.
I'm thinking of someone taking over your flash, and you're basically asking the BMC what's your flash, So that could be compromised. The answer to that would be the BMC answering, which could be compromised. So my question is, would it make sense to expose the SPI port so that you could go with an SPI interface reader to verify the flash itself?
So I'll add two angles to the answer here. I don't think it's a how did you call it, a fool's errand? Fool's errand? Yeah. I don't think it's that, but there are two issues that comes to mind here. One, what you're proposing seems to indicate you want to go physically to the server and read the flash.
Yeah.
And in cloud scale, that doesn't happen, right? We cannot go physically to a million server.
If you have a compromised server, it's reasonable that you don't throw it away.
Yes.
Right, but still, like, how would you even do that at scale? That's really the first the question that comes to my mind. Like, if you have many servers and many ports, how do you do that at scale? And
But the question is, how do you do it at all right now?
yeah. So the second thing I wanted to say is, when we are working before even Cerberus, when we are working with our providers, we do require, and sometimes the requirement can be met, and sometimes it's hard, but we do require the ability to read flash completely. So we want to be able, if we put a disk in the system, we want to have a way to read the entire image of the flash memory. And yes, sometimes a very sophisticated attacker can actually fake even that, which is one of the reasons why we're asking to read the entire flash and not just give us a hash, because that's easier to fake. And Cerberus will actually do it for us in a much more trusted way, right? So our approach to that is require the ability to read the flash and not a physical port.
Okay. Thank you.
Yep.
You can hand off the mic to him. And
Thank you. I sometimes have, doubts in putting on more hardware, complicated hardware, to make stuff like SPI flash, which is pretty simple in theory, more secure. Obviously, yes, you have the problem that without any security, or if some attacker manages to bypass existing security, you want to check what's going on, but do you really think adding another chip or putting in more hardware, complicated hardware, including software, is really going to help, except making it harder to go the original exploitation way and making it maybe easier by opening up another way by accident?
So I think if you want security, the most secure you can get is just pull the power cord and leave the system there. But of course, that's not usable security. So I agree with you completely. Adding components to a system inevitably changes your AFR, your reliability. Adding more components, decreases the reliability because it increases the probability of one of those components failing. But your alternative is no security. So it really becomes, where do you rate your security? Of course, you make your components that you're adding, you make sure that they are reliable and that you're not compromising on your reliability or your availability, but instead you're ensuring that reliability is good and adding the security that's missing. So, if you want to have reliability, take all the DRAM out of the system, don't put it in there. Take all the hard disks out of the system, don't put it in there, but then you don't have a very useful system. We view security as the same. If you don't have security in a system, you don't have a very useful system. So it's a trade-off. It's a tough choice to make. But yes, you're adding components, you just make sure that the reliability is very good. You always have a fail-safe and fail securely if that component doesn't operate in the way you expected it to operate.
I think I'll add one more point to that, which is Cerberus is three things, right? It's a design principle for the system. It's a set of requirements to how to enforce security. And the chip is a way to implement that if you cannot do it without it.
Yes.
So if you want to go like the easy route, there will be a chip, you can use it. The preferred approach is if you actually implemented all of the requirements correctly into the system, and then we don't need this chip. But we are trying to be pragmatic about how to get a system that wasn't always designed with security in mind to be secure, like faster. and we developed this chip ourselves, and we do trust ourselves to follow good security practices. And again, it can be a controversial point whether it's the right thing, it's like the ideal thing or not, but it's a pragmatic thing.
Thank you.
Any other questions? And then you.
Can you explain I think mostly for Bryan, can you explain the hierarchical approach when you have a peripheral that has an embedded controller for which Cerberus is not in the flash path at all? I think you had one slide on that, on the hierarchical master-slave.
This here, this
Yeah.
slide.
Yep.
So the question, what was the question?
So if I have, say, a NIC that has its own firmware,
Yes.
Cerberus is not in the path to that firmware, how can you
Oh,
secure that thing?
you're talking about peripherals where the firmware is internal on the ASIC.
Either internal or discrete, but doesn't go through Cerberus.
Yeah. So if that NIC met the security requirements that we defined, and it had secure boot, had attestation, and had that attestation protocol to be able to exchange those measurements back in a secure way, then it would intrinsically have Cerberus in it. It would intrinsically have the same Cerberus functionality in it.
I think you're asking about
No.
the protocol between those Cerberuses and how they talk to each other.
Oh yeah, that protocol that we have here is an I2C path that we run. The I2C path is there anyway, going out to the device. We chose the protocol between Cerberus is I2C. We chose that because that path exists for cooling. It's already there for temperature probing. We just piggybacked on that one. It's available pre-boot. It's available on systems that don't have host processors, which we have as well. So it's kind of a universal interface that gives us the most coverage in our platform. So I don't think I explained that earlier, but that interface going down is an I2C interface to the peripheral, and off of that we talk to the Cerberus chip, or if the functionality is intrinsic inside in the processor, we would then talk with the processor and take its measurements back.
I think you have also a backup slide on that, right? So the slide deck will be available, and there are additional slides with more details
Yes.
on these things.
I think he was next.
And then I think he's got a question.
So, how does the root of trust extend to the root of trust for the x86 or the BMC? That is there a communication path and a protocol for the measurements and the PCR-like things to be communicated securely to the CPU so that it can use that as part of its remote attestation to whatever other systems it's talking to?
So I think you're asking about the systematic level. How do we basically extend the measurements from Cerberus into the TPM? Would that be a reasonable rephrasing of the question? So yes, so the Cerberus extends a single measurement into the TPM and has its own set of measurements. And when we do attestation for a system, we basically ask the TPM to give us the log, and then use that to calculate what are the right hashes. And when there is a Cerberus in the system, we also take a similar set of TCG-like log from Cerberus and compare that to the Cerberus measurements. So we end up, and the way it works in Azure is that if you want to attest and prove your healthiness, you give us the log, and we basically seal a certificate back to the host that the TPM will open up only if the measurements match. Okay? And when Cerberus is in the system, we actually do it twice.
And does the Cerberus have a per-device public key that has some sort of endorsement key signed by Microsoft or someone?
Yeah. Similar to the TPM that has the AK. Yeah. So it's kind of like today it's double verification, like the TPM and Cerberus. Both of them are similar, but the Cerberus measurements are more trustworthy than TPM ones, because TPM doesn't do anything active. It trusts whatever you report into him. Cerberus actually takes the measurements. Okay. Any other questions? You, and then you can. Yeah.
So my question is, the key that you'll be provisioning into the Cerberus, you said that's this Microsoft supplied key that'll be used as a certificate generation key?
So there are two keys. Two keys at provisioning. One is a public key that just gets fused into eFuses, and that's for authenticating the key manifest, the little table that's part of the first piece of mutable firmware. That key gets authenticated with that public key. That public key is of course, it's just a public key. It's common on a lot of chips. Each Cerberus will generate its own key. It generates using a measurement of mutable firmware plus some entropy, and that puff plays into some of that entropy. It will generate its own key, and we'll keep the private key private to that chip, and it will give out the public key. Well, actually, we'll build out a CSR and give out a CSR. A CSR will be harvested at silicon verification time. So when they're manufactured, you go through a process of verifying the silicon is sound and binning silicon that's not sound. Obviously, you want to have good yield, and it gets back into the reliability question earlier. So you want to have high yield there. As you're going through that silicon verification for each chip, you're also harvesting the CSRs, and you take those CSRs, and then at a later date, you sign them, you're turning them effectively into certificates, and you're returning them back to the device. And those certificates are device unique. The certificate that issued the CSR has to get back the certificate that corresponded to its CSR. Right. And at that time, it's a signed certificate that we assign back to the device. And that can be later in its lifetime, or it can be at manufacturing. There's flexibility around that. The harvesting should be as early as possible. The returning of a legitimate certificate, signed, CSR that's actually carries a signature with it, that can be returned back at a later point in time. Okay. But only the chip that has that private key can respond to a challenge for that certificate.
So every chip will have its own private key?
Chip unique, yeah.
Okay.
Yeah.
Thank you.
So there's no
Let me do it for
clone one, clone them all, or crack one, crack them all scenario.
Thank you. Given that you mentioned the endorsement key, I know that it's usually quite unpopular to have the endorsement key hierarchy replaced. There is some, sort of process where you assume that the supply chain will not be tampered with at the original chip manufacturer, and so the endorsement key is a good idea until then. But once you start making these chips part of your own infrastructure as the consumer, then you might want to resign all that stuff and replace the endorsement keys and everything to make sure that if the hardware is not being endorsed by you, even if somebody else could compromise, for example, the supply chain in between, they would still it would still be noticed that something has changed. So do you foresee such a way to replace the endorsement key in that case, or regenerate it, re-endorse it at the customer side?
Yes, that is possible. And the key is a combination of some entropy from the chip and the measurement of the first part of mutable firmware. So this, if you consider the ROM, the first stage bootloader, the second stage bootloader, that measurement plays into that key. So it ultimately plays into the certificates that are derived from those keys. So if you wanted to replace an endorsement key, the only thing you'd have to do to get a fundamentally different endorsement key is change a single bit in that first part of mutable code. If that gets changed, the key is that the keys that get generated and the certificates that get generated that correspond to those keys is fundamentally different. It's true to the nature of HMAC.
Thank you.
Yeah.
Is it possible to generate your own mutable firmware? So,
Yes.
You said that there's a fuses that are used for authenticating the initial stage bootloader, and then is it possible to either is it possible then to replace the mutable stage with customer code?
It would be possible, yes. That mutable code can be completely removed from the chip, but then you're getting completely different certificates out of the chip. They're not going to correspond to the signed certificates that you get back the chip. So in that stage, it has to be re-enrolled. If you want to use TPM language, it would have to be re-enrolled, and it would spit back out a CSR, and you'd have to go sign it and say, yeah, I trust it. Here's your code. Now, there's also the secure boot key, which is put into eFuses, and we use the secure boot key on the key manifest. So we don't only do a measured boot with Cerberus, we also do a hardware secure boot using RSA signatures. And that key has limited replacement options. So there's a limit to the amount of times you can revoke that key. And of course, as a consumer, if you were to go out and buy a Cerberus, you would then have to make sure that was fused with your own key.
And that limit is more than one,
Yes.
but
Yeah.
less than
Yeah, I think it's
1,000.
I think it's like it's 4 or 8. It's somewhere in that region. I think it might be 8, but I think it might have started out as 4 and then went to 8.
Any other questions? Okay, so thank you very much. And I really encourage you to
Sure.
please join the work group.